So now we're on linear kinematics 3. This is just a continuation of the study of motion in a straight line. We'll be talking about position, velocity, and acceleration in one dimension. We've talked about a bunch of these things already today. In this slideshow, I'm going to give you a few more examples and a few more useful equations in terms of ones we've already developed. So let's begin by just coming up with another useful equation or two. We can start with things we already defined. We said the average velocity is just the change in position divided by the change in time. Right? That's how we defined the average velocity. We can rearrange this to get the change in position in terms of the average velocity and the time. Hopefully you can see the algebraic step that was taken between these two to get to solve for delta x. Now, we also said there's another way to write the average velocity. It's the initial velocity plus the final velocity divided by 2. And so in this equation for delta x, we can replace the average velocity there with v1 plus v2 divided by 2, and we get this equation on the next line. Delta x is v1 plus v2 divided by 2 times delta t. Okay. So now we can look at the acceleration. Hold this one in your head a little bit, and we can talk about the acceleration. The acceleration is the change in velocity over the change in time. And just as we solved the average velocity in terms of position, we can solve the acceleration for the change in velocity. And so we can say the change in velocity is equal to the acceleration times the change in time, or v2 minus v1, that's the change velocity, is equal to the acceleration times the change in time. And then we can say, well, v2 is just v1 plus the acceleration times the change in time. And so now we're going to do a little tricky bit of mathematics on this next slide. But what we're going to do here is we're going to take this piece here, v1 plus acceleration times the change in time, and stick it up here for this change of position for the v2 in there. Since v2 is equal to v1 plus the acceleration times the change in time, those two are equal. This is like saying 5 is equal to 3 plus 2. Anywhere I have a 5, I can replace it by a 3 plus 2. And so what we've done is we've looked at this v2 here, and we're going to replace it with v1 plus a times delta t. And so you'll see that on the next slide. Right? I just rewrote that top line, the last few lines there. We get v2 is equal to v1 plus the acceleration times the change in time. And now we're going to substitute into this equation, and it looks like this. The change in position is equal to v1. Instead of plus v2 over 2, it's plus v1 plus the acceleration times the change in time over 2 times the change in time. And if you do some algebra on that, you just sort of work all that out. What you end up with is the change in position is equal to v1 times delta time plus 1/2 times the acceleration times the time squared. Okay, this expression here is just an algebraic solution. I don't know if I call it a solution rearranging. You can look at this expression here, and so let me just work this out on the blackboard here for a second, and I'll just show you what we're doing. So if I write that expression, delta x is equal to v1 plus the acceleration times the change in time all over 2 times the change in time. I can first just look at the numerator. I can say delta x is equal to, so that's just v1 plus the acceleration times the change in time. All over 2 times the change in time. But that's just equal to 2 times v1, because v1 plus v1 is just 2 times v1, plus the acceleration times the change in time, all over 2 times the change in time. And this change in time is actually multiplying the whole thing, right? This guy on the outside multiplies everybody on the inside. Well, if I just want to look at this expression in parentheses, right, delta x is equal to, if I take this into a lot of steps, this is 2v1 over 2 plus the acceleration times the change in time over 2. Anytime you have, if I write 4 plus 6 over 2, that's just 10 over 2 is equal to 5. I can just as easily write that as 4 over 2 plus 6 over 2, which is equal to 2 plus 3, which is equal to 5. All I've done here is just a little bit of fraction math, and you may not remember that very well, but that's all it is. I'm not going to ask you to regurgitate this or memorize it, and if I give it to you on a test, you'll have these equations on a sheet of paper with you. So you don't have to worry too much about it, but I want you to see where this comes from, or at least know where it comes from. Delta x is equal to, so the 2's cancel, and I just get v1 plus the acceleration times the change in time over 2 times the change in time. And since I can multiply this through, it's called the distributive property, if you remember your math. This is v1 times the change in time. I multiply this guy by this guy, plus acceleration times the change in time over 2 times the change in time. All right, and this is equal to v1 times the change in time plus 1/2 a times the change in time squared, like that. Because I have a change in time times the change in time. And so that's what my change in position is. Sometimes this is just written this way. D equals, right, the distance traveled, or the change in position, is equal to v1 times delta t plus 1/2 a times delta t squared. And so if we go back to the sheet here, there, that's what you see down here at the bottom, right? And the cool thing about this, or the useful thing about this, is that if you know your initial velocity and what your acceleration is, and then you can just pick any time, how long do I want to know how far it's traveled, right? I can get how far it's traveled if I know the initial velocity, what this acceleration is, and how much time I'm interested in letting pass. So now we can do an example. We have a car. Suppose a car is traveling at 4 meters per second, right? At t1 equals 2 seconds, and then it accelerates to 10 meters per second 3 seconds later at t2 equals 5 seconds. We can just ask a few questions. I can say, well, what's the car's acceleration? Well, that just takes us back to our original equation, which is the definition of acceleration. It's the final velocity minus the initial velocity, so 10 minus 4 over the final time minus the initial time, which is 5 minus 2, so it's 6 meters per second over 3, or 2 meters per second squared. Right? How far does the car travel in this time? Well, we can use this formula we just had, right? Distance is equal to v1 times t plus 1/2 times a times t squared. Notice I didn't write the delta t there. I'm just saying that t represents the time it's spent traveling. You'll see down here I write t1 is just delta t. I'm just using it as a name for a different thing. And that's just how much time it's spent traveling, t2 minus t1, or 5 seconds minus 2 seconds, or 3 seconds. The acceleration we determined up above was 2 meters per second squared. And so now I just say v1 is 4 meters per second times 3 seconds plus 1/2 times 2 meters per second squared times 3 seconds all squared, right? And so if we do these piecemeal, 4 times 3 is 12. The seconds cancel like meters, because this second is in the numerator and this second's in the denominator, right? Similarly here, I get 2 times 1/2, which is 1, and 3 seconds squared is 9 seconds squared. The second squareds here cancel the second squared, so I get 9 meters, so 12 meters plus 9 meters is 21 meters. And so this car has traveled 21 meters while accelerating from 4 meters per second to 10 meters per second over the course of 3 seconds. Oh, maybe I do that. We could solve this one slightly differently, and I'll just do it on the blackboard here, or maybe the whiteboard. Right? If I go to that same problem, let's see if I can just wipe this off really fast. Nope. So let me try it like this. now like that. That's pretty close. All right. We could have also said that the change in position, remember, we're asking how far the thing went. Oh boy. So let me see if I can get my focus back. All right, I'm going to write here for a minute and see if the focus comes back in. I think it will. There we go. So if you remember, we said V average is equal to the change in position over the change in time. And so that led to the change in position is equal to V average times the change in time. In this problem, we said V1 was equal to 4 meters per second, and V2 is equal to 10 meters per second, right? And so V average, based on our other definition of average velocity, is V1 plus V2 divided by 2. In this case, that's 4 meters per second plus 10 meters per second divided by 2, which is 14 meters per second over 2, which is 7 meters per second. And now when I rearrange this to this, I get delta x is equal to V average times delta t. This is just 7 meters per second times 5 seconds minus 2 seconds, which is 7 meters per second, times 3 seconds, which is 21 meters. That's exactly what we got solving it the other way, right, on the last slide. So you can solve that either way.